So it happened again where I made a video, got all done, ended the recording, and the program crashed on me. Something I really got to get figured out because it's kind of driving me a little bit crazy. I know you don't care, but I like to complain. A bunch of the work that you see in front of you, I need to erase and redo in this video. Alright, so in the last video that you saw, what we worked on are limits at points of discontinuity. We learned about 3 different types of discontinuity and talked about how often when you're evaluating limits at points of discontinuity, you're going to want to consider 2 different one-sided limits so that you can evaluate the two-sided limit. We saw that in the case of jump discontinuities, the 2 different one-sided limits are going to disagree, which makes the two-sided limit undefined. However, in the case of a removable discontinuity, the 2 different one-sided limits give you the same value, and that value is how we define the two-sided limit. The case when you have a removable discontinuity is going to end up being the most important case for our class. However, we're rarely going to see it in its geometric form. Instead, we're going to see it in its algebraic form. Occasionally, you'll see jump discontinuities algebraically. That's what we saw in these 2 examples in the last video. But far more common will be removable discontinuities algebraically. And that's what I want to go over in this video. There's 4 examples on this page, and then there's another one I want to go back to that we've seen on previous pages, and I want to do all those in the same video. So all I'm going to do in this video is talk about evaluating limits at points of discontinuity, where that discontinuity is a removable discontinuity, and the function that we're evaluating the limit of is a rational function, meaning a quotient of 2 polynomials. So it's the case you see in A and B here, but not the case you see in C and D. So how do you do such things? Well, first, I want to remind you of something that you probably knew when you took a pre-calculus class, but may or may not remember now. If you have a polynomial, so like 2x squared minus 3x minus 9, or 2x squared minus 18, or 2x minus 2, or x cubed minus 3x squared plus 5x minus 3. If you have a polynomial and there's a value that you can put into that polynomial and make 0 come out, that value is what's called a root of the polynomial. Maybe so this is less abstract, I'll pick a specific polynomial. F of x equals 2x squared minus 3x minus 9. Note what happens when you put 3 into this machine. What comes out would be 2 times 3 squared minus 3 times 3 minus 9. 3 squared is 9, 2 times 9 is 18, so I get 18 minus 9 minus 9, I get 0. When I put 3 into this machine, 0 comes out. Numbers that you put into polynomials that cause 0 to come out get a special name. They're called roots of the polynomial. So 3 is a root of this specific polynomial. An important theorem, often referred to as the fundamental theorem of algebra, states that if 3 is a root of some polynomial f, then x minus 3 must be a factor. And that kind of makes sense, right? If I were to take this polynomial and factor it, so rewrite it as something times something, I know that when I put 3 into this factored form, 0 comes out. So how could I put 3 into a factored form and have 0 come out? Well, the factored form is something times something. And the only way you can get a product of things equaling 0 in math is if one of those things itself is 0. So how is one of these factors going to be equal to 0 when I put 3 into it? The factor must be x minus 3. The only way I can get 0 out of a factor when I put 3 into it is if that factor itself is x minus 3. So maybe if I was really good at factoring, I could just look at this thing and factor it as x minus 3 times something else. But even if I wasn't really good at factoring this thing, the minute I realized that putting 3 into this machine caused 0 to come out, I would immediately know one of the 2 factors that comprises this polynomial. And sometimes after you find one of the factors, it's a lot easier to find the other factor, right? What must go in this set of parentheses? Well, there's got to be a 2x here because this x times this 2x would give me the 2x squared. And there has to be a positive 3 over here because this negative 3 times this positive 3 would give me the negative 9. I don't have to do the same level of analysis to factor this polynomial if I start out by knowing one of the 2 factors. And because 3 was a root of the polynomial, I knew one of the 2 factors. That's really important. Why? Because when we're evaluating these limits, the limits we'll be concerned with in our class are those that are approaching points of discontinuity, specifically removable discontinuities. If this expression has a removable discontinuity at 3, what that means is when I put 3 into this machine, 0 divided by 0 is going to come out. Maybe you recall from pre-calc that when you have rational functions, numbers that make the top 0 but not the bottom 0 are x-intercepts. Numbers that make the bottom 0 but not the top 0 are vertical asymptotes. And numbers that make both the top and the bottom 0 are holes, loosely speaking. Removable discontinuities are just holes, so they'll arise at values that make the top and the bottom 0. What I'm saying is pretend you walked into a quiz and you got this problem right here. If you're evaluating this limit, you're hoping that this expression as a function is continuous at 3. Because if this expression as a function is continuous at 3, then we're at our very first example where evaluating the limit is super easy, right? To evaluate the limit at a point of continuity, all we got to do is plug that number 5 up into the function to get our answer. If you're fortunate enough for me to have given you a function here that's continuous at 3, well then your work's going to be really easy. Spoiler alert, you're not going to be that lucky. But you might as well try. Let's take this expression right here, give it a name, maybe f of x for example. And then let's evaluate f of 3 by changing all of the x's in this expression into 3's. 3 squared is 9, 2 times 9 is 18, 18 minus 18 is 0. 3 squared again is 9, times 2 is 18, minus 9 more is again 0. When I put 3 into this machine, I get 0 over 0. I get this undefined output. You're probably thinking, oh, that's too bad. That's bad news. That makes it hard to evaluate this limit. And yeah, kind of, but it's not all bad news. It gives you some good news. The fact that 3 made the top and bottom 0 means that 3 is a root of the polynomial up on the top, and it's also a root of the polynomial down on the bottom. What that means is the polynomial up on the top can factor to x minus 3 times something. And the polynomial down on the bottom can factor to x minus 3 times something. We've already done that factoring of the polynomial down on the bottom over here. It's x minus 3 times 2x plus 3. We haven't done that same analysis to the polynomial on the top, but maybe now we can figure out this factor. What goes here? There's got to be a 2x here because this x times this 2x gives me the 2x squared. What goes here? There must be a positive 6 here because the negative 3 times the positive 6 gives me the negative 18. All I've done is factor the numerator and the denominator, so I haven't changed the value of this expression, so clearly this limit is the same as this limit. I'm just writing it a different way. But this limit, this second one, is a lot nicer than this top one. Why? Because I can cancel out the x minus 3's. Kind of. If I were to cancel out these x minus 3's, all I would have left up on the top is 2x plus 6, and all I would have left down on the bottom is 2x plus 3. The nice thing about this expression is it's really easy to evaluate this limit. Don't believe me? All you got to do is change all the x's into 3's. Why? Because this expression is continuous at 3. When we put 3 into the machine, we don't get an undefined output, so evaluating the limit is simple. We get 2 times 3 plus 6 divided by 2 times 3 plus 3. We'd get 12 ninths, in other words, 4 thirds. The limit as x approaches 3 of this expression is 4 thirds. And because this limit is the exact same as this limit, which is the same as this limit, the answer to this question is just 4 thirds. 2 comments. I don't want to confuse you here. So when you're taking your quiz, you follow through these steps, you write exactly what you see in front of you, you get full credit, you don't have to worry about anything. However, I'd be remiss if I didn't give you a little bit more information. This equal sign right here is a little bit suspect. Why? Because this expression that you see in red here is not the same as this expression that you see in green here. They're very similar, but in order for them to be the same, no matter what number I plug into this thing, I have to get the exact same answer if I plug this number in down here. So I don't know, try plugging in like 4 or something and see what comes out. And what you'll see is what comes out here is the exact same as what comes out here. What about 5? What about 6, 10, 100, pi, e? You throw in all these numbers, you're getting the exact same thing here as you're getting here. So you're feeling really good. Like red's the same as green. I keep getting the same output no matter what I put in. But then you try plugging in 3. If you plug in 3 up here, you get 0 over 0 because 3 minus 3 is 0 and 0 times anything is 0. Same idea down on the bottom. If you put 3 into this expression in red, you get an undefined output. However, if you put 3 into this expression in green, you don't get an undefined output, you get 4 thirds. Because you get different outputs when you plug in 3 to the expression in red and the expression in green, those expressions are not equal. And you're like, whoa, then why did you put an equal sign here? The expressions are not equal, but the limit as x approaches 3 of the expressions are equal. Wait, what? What's going on here? When you cancel out these x minus 3's, all you're doing is getting rid of that hole that was at x equals 3. If you look at this graph and you look at this graph, they'll look identical, except this graph will have that hole at x equals 3. It's really analogous to the first two examples we saw in this section. This polynomial f of x is x squared minus 3x minus 2. This polynomial g of x is x cubed minus 8x squared plus 13x plus 10 divided by x minus 5. No way those are at all related, right? Turns out they are. If you take g of x and you factor it, and I'll show you these steps in just a minute, what you end up with on the top is x minus 5 times x squared minus 3x minus 2. Don't believe me? Multiply these polynomials back together and you'll recapture exactly what you see in the numerator here. How did you know x minus 5 was going to be a factor? Because look at what happens when you plug 5 into that polynomial up top. 0 comes out. That means 5 is a root of the polynomial up top, which means x minus 5 must be a factor. And because I already have an x minus 5 in the denominator, I can cancel out these two x minus 5's, and what I'm left with is just x squared minus 3x minus 2. Wait a minute, x squared minus 3x minus 2, that seems really familiar. Where have I seen that before? That's exactly the polynomial that we have up here, x squared minus 3x minus 2. This graph f of x and this graph of g of x are identical. The only difference is this one has this open circle at 5. Essentially, when I go from this expression to this expression by canceling out these x minus 5's, what I'm doing is filling in this open circle right here. I'm not changing any other points on the graph. I'm just getting rid of that removable discontinuity. But that's really helpful because when that removable discontinuity isn't there, I'm evaluating a limit at a point of continuity. And evaluating limits at points of continuity is really easy, right? To figure out this limit, since this function's continuous here, all I got to do is change all my x's into 5's. Without seeing the pretty pictures, what we're doing down here in these steps is we're factoring this rational expression so that we can cancel out the x minus 3's. Why do you want to cancel out the x minus 3's? Because essentially what that does is it fills in that open circle. It changes the graph from having a removable discontinuity at x equals 3 to being continuous at x equals 3. And when the graph is continuous at x equals 3, evaluating the limit is super easy. You just change all the x's into 3's and get your answer. Most students, frankly, never learn that in a calculus class. They just write this equal sign and never really think about it. But I feel like I'm doing you a disservice if I don't make the point that this expression is different than this expression. So if you're not writing limit as x approaches 3 in front of these, you really can't write this equal sign right here. And if you don't write this equal sign, then you can't go through this series of steps to figure out what this limit is equal to. So make sure you're writing limit as x approaches 3 before these expressions. Otherwise, this one is not equal to this one. There's a few things I need to clean up before I move on to this second example in this video. It deals with this function g of x, which was x cubed minus 8x squared plus 13x plus 10. And I said it factors to x minus 5 times x squared minus 3x minus 2. And I was like, don't believe me? Like, multiply them back together and prove it to yourself, which is a really unsatisfying thing to do. Even if you could multiply those back together, that doesn't show you how you get here in the first place. Like, from the student's point of view, if you were trying to evaluate the limit as x approached 5 of this expression and we weren't lucky enough to have the graphs, would you be able to do it? And the answer is yes. What you would do is you would check to see if this expression is continuous at 5. Hint, it's not going to be. You're going to plug in 5 and you're going to get 0 over 0 because all of the expressions that we'll be interested in their limits will be this type with removable discontinuities. But when you get that 0 over 0, that's actually good news because that tells you that x minus 5 must be a factor of the top and the bottom. And the bottom is pretty clear. It's just x minus 5, times 1 if you want. But in the top, it's not at all obvious that x minus 5 is a factor of this third degree polynomial. You need to factor this third degree polynomial so you can cancel out those x minus 5's. So how do you find the other thing, the x squared minus 3x minus 2? Or there's a few different ways you can do it. If you're familiar with synthetic division, you can do it that way. You can kind of just talk yourself through it being like, I need an x cubed, so there must be an x squared here, and x times x squared gives me the x cubed, but there's a problem when I put an x squared here, I get negative 5x squared. but I'm supposed to have negative 8x squared. So there must be a negative 3x here, so that the negative 3x and the x gives me negative 3x squared, which I can add to the negative 5x squared that I already had to get the negative 8x squared. You can kind of continue with those series of steps to come up with this polynomial here. A third way that you can do this, which is probably the way that I would do it, is polynomial long division. Maybe something that you learned in a pre-calculus class. You know that x minus 5 is a factor of this polynomial, x cubed minus 8x squared plus 13x plus 10. How do you know it's a factor? Because 5 was a root. How do you know 5 was a root? Because when I put 5 into this polynomial, 0 came out. I put in 5, 0 comes out. 5's a root. If 5's a root, x minus 5 is a factor. If x minus 5 is a factor, then when I do polynomial long division, I'm going to get 0 as my remainder, and my quotient will be what I need to multiply x minus 5 by to get x cubed minus 8x squared plus 13x plus 10. In case you don't remember the algorithm, I'll show you really quick. What you're trying to do is always get rid of the leftmost column. So my leftmost column starts out being x cubed. I want to get rid of x cubed. How am I going to get rid of x cubed? Put an x squared up at the top. Why? Because the next step in your algorithm is to take whatever you wrote up top and multiply it by the x minus 5. So x squared times x minus 5 gives me x cubed minus 5x squared. And then what I have to do is subtract the second line from the first line. X cubed minus x cubed goes away. I've gotten rid of the first column, which was exactly what I was trying to do. Negative 8x squared minus negative 5x squared. Be a little careful here. That's the same as negative 8x squared plus 5x squared, which is negative 3x squared. I bring down that 13x and I repeat my algorithm. Now my leftmost column is this negative 3x squared. I want to get rid of that. How am I going to get rid of it? By putting a negative 3x up top. Why negative 3x? Because negative 3x times x minus 5 gives me negative 3x squared plus 15x. Again, I'm going to subtract. Negative 3x squared minus negative 3x squared goes away. 13x minus 15x leaves me with negative 2x, and I bring down the plus 10. I want to get rid of this negative 2x. How? By tossing a negative 2 up top. Negative 2 times x minus 5 gives me negative 2x plus 10. I subtract. This column goes away, and this column also goes away, which means I have 0 remainder, which is a nice built-in check, and tells me that x cubed minus 8x squared plus 13x plus 10 can be rewritten as x minus 5 times x squared minus 3x minus 2, exactly the factoring that I did right here. So if you started out with this problem, you could do this polynomial long division, which would allow you to write the top in this factored form. Then you could cancel out the x minus 5s as long as you're writing the limit as x approaches 5 out in front here. That allows you to say that this limit is the same as the limit as x approaches 5 of this expression. Good news about this expression is continuous, so to evaluate the limit is really easy. Just change all the x's into 5s. You get 25 minus 15 minus 2, which is equal to 8, which is exactly what we see happening when we look at the graph. This graph with the open circle is this function. This graph without the open circle is this function, x squared minus 3x minus 2. They're almost identical, just one has the discontinuity. Not sure you were able to follow all that? Let's do one more example and then we'll call this video good. Suppose I asked you to evaluate the limit as x approached 1 of 2x minus 2 times x cubed minus 3x squared plus 5x minus 3. Not a horrible idea to try this on your own. It would be pretty hard, but you might want to give it a shot. Maybe first give this expression a name. What do you want to call it? I don't know, whatever letter you want. Maybe I'll do g of x this time just to mix stuff up. If g of x is 2x squared divided by x cubed minus 3x squared plus 5x minus 3, I want to evaluate g of 1. Why? Because I want to see if this expression is continuous at 1, because I'm evaluating the limit as x approaches 1, and if this limit just so happens to be continuous, then evaluating the limit is going to be super easy. But again, spoiler alert, it's not going to be continuous there. You're going to get 0 over 0. Don't believe me? 2 times 1 minus 2, sure enough, equals 0. 1 cubed minus 3 times 1 squared plus 5 times 1 minus 3 is 1 minus 3 plus 5 minus 3, which sure enough is 0. When I put 1 into this expression, 0 over 0 comes out, which is undefined. So I can't immediately figure out the limit as x approaches 1 of this expression. But what I do know is that 1 is a root of the polynomial up on the top, and that 1 is a root of the polynomial down on the bottom. And that's super useful information to have, because if 1 is a root of a polynomial, then x minus 1 must be a factor of that polynomial. What I'm saying is I can rewrite the top as x minus 1 times something, and I can rewrite the bottom as x minus 1 times something. What is that something up top? Well, up top is pretty easy, right? If you just factor out a 2, you get 2 times x minus 1, or x minus 1 times 2 if you prefer to write it that way. What about down on the bottom? Well, that's a little bit less obvious. If you're really good with polynomials, you might be able to just kind of look at this and be like, well, there must be an x squared here, because x squared times x gives me x cubed. But the problem is x squared times negative 1 gives me negative 1x squared, and I'm supposed to have negative 3x squared, so there must be a negative 2x here. And the negative 2x times the x will give me the other negative 2x squareds. But there's a problem with the negative 2x. Negative 2x times negative 1 gives me positive 2x. But I'm not supposed to have positive 2x. I'm supposed to have positive 5x. So there must be a plus 3 here. This 3 times this x will give me the 3x, which I can add to the 2x that I get from the negative 1 times the negative 2x to get 5x. And sure enough, the negative 1 times the 3 gives me the negative 3. In case that's uncomfortable for you, you can also use polynomial long division, where we do x minus 1 divided by x cubed minus 3x squared plus 5x minus 3. First goal is get rid of the x cubed. Do that by putting an x squared up here. X squared times x minus 1 is x cubed minus x squared, and you subtract. When we subtract, the first column goes away. That's good. Negative 3x squared minus negative x squared is the same as negative 3x squared plus x squared, which was negative 2x squared, and I bring down the 5x. Note that if you're going to make a mistake, it's probably right here. You're probably going to write negative 4x squared right here instead of negative 2x squared. Make sure you're subtracting the negative. You want to get rid of this negative 2x squared, just top a negative 2x up top, because negative 2x times x minus 1 is negative 2x squared plus 2x. And when I subtract again, the leftmost column goes away, and I'm left with just 3x. I bring down the negative 3, and I get rid of both of these by putting a plus 3 up top. 3 times x minus 1 gives me 3x minus 3. I subtract, everything goes away. I got a 0 remainder. It's a nice little check. It tells me that this polynomial can be rewritten as x minus 1 times x squared minus 2x plus 3, the same thing that I got over here. It's easy to get lost in what you're doing. Remember, our goal is to evaluate the limit as x approaches 1, but we can't evaluate it immediately because this function is not continuous at 1. There's a removable discontinuity there. What that means is we have to factor it so that we can get rid of that removable discontinuity. The magic happens in this next line. This limit is the same as the limit as x approaches 1 of 2 divided by x squared minus 2x plus 3. This expression is not the same as this expression, but their limits are the same. If you graph this expression and you graph this expression, they'll look almost identical. The only difference is this one will have an open circle at x equals 1, and this one will not have that open circle at x equals 1. All we're doing when we go from this line to this line is we're filling in the open circle. Now that we've filled in that open circle, this function is continuous at 1, so evaluating this limit is super easy. When a function is continuous at the point you're trying to evaluate the limit at, we take advantage of the fact that the limit is the same as the function's value at that point. So if we wanted the limit as x approached 5 of f of x, we just evaluate f of 5. If we instead want the limit as x approaches 1 of this function, we just evaluate this function at 1. Change all the x's into 1s. What do we get? We get 2 divided by 1 squared minus 2 times 1 plus 3. 1 minus 2 plus 3, that sounds like 2 to me. 2 divided by 2, that's equal to 1. This limit is equal to 1. The algebra is pretty tricky. I mean, all these different steps that we're doing are hard, and it'd be really easy to make a little mistake in here. But at the risk of sounding super nerdy, what you're doing here is super interesting, right? The way you're changing these different lines is not just the typical pushing symbols around on a page. You're doing this very intentionally. This equal sign here is super subtle because this expression is different than this expression, but their limits are the same. This idea of filling in open circles so that you can evaluate limits is pretty deep and pretty fascinating. And it's what you'll need to do anytime you're evaluating a limit at a point of discontinuity where that discontinuity is a removable discontinuity. And hint, the case we're going to be interested in this class is exactly that. I'm supposed to teach you about all sorts of discontinuities in this section, which is why I drew all these different pictures for you and showed you all the different types. But the type that's going to be relevant in our class is this type right here, when we have the removable discontinuity. And what we're always going to be looking at is the limit as we approach that removable discontinuity. And what we're always going to do to figure out that value is, loosely speaking, fill in the open circle so that the function becomes continuous, and then evaluate the limit by just looking at the height of the function at that point. I'm going to end this video here, and if I get this same warning that the program unexpectedly quit and I have to re-record, I might just throw my laptop out the window.